我们开始吧。首先我们复习象字的内容。象字我们学过这个黎曼流行，然后黎曼流行像我们可以定义一个球线的强度，曲线的强度。在黎曼流行上有强度的意义，然后用黎曼这个是度量。所以用度量，我们可以定义这个 orthonormal system。So orthonormal system is the so at the point one can always find the metric such a way that you can always diagonalize, and then G E I E J is equal to delta I J 这样的渐交表价orthonormal frame at each point. So at each point, you can always find the E1, E2, of normal vector at each tangent space, at each point you can find. So 减项标价。如果我们有建交标价的话，我们可以定义 Hodge， Hodge 新算子 Hodge star。So Hodge star， 的定义是如果我们有这个度量，我们可以定义这个 Hodge star。So ordinary manifold, if you don't have the metric, you cannot define Hodge star. Hodge star always you need to have a metric. Okay. And then, so the volume form is given by square root g dx. Okay. And then alpha. 如果你有 Hodge star 的话 ，so this Hodge star will map omega k to omega n minus k。Okay. So 这个微分形式 degree k to 到 n minus k。重要的性质是Hodge star square is equal to minus 1 to the k n minus k identity。然后我们可以定义与微分算子 delta is the minus 1 to the some power which is not so important and star the star which map omega k 到 omega k minus 1。就是与微分算子，以微分算子的性质是delta square is equal to 0， 然后delta square equal to 0， 然后 number 2是这个是半水算子d y 微分和 delta 是半水算子，比如说 d alpha beta is equal to alpha delta beta。Here the pairing here is given by alpha beta pairing is given by, so the alpha and beta of both omega k is given by like this Hodge star pairing。所以这个是Riemann 流行上的内积，所以这个y 跟 微分形式上的内积，然后用这个内积，我们可以说 d 和 delta 是对半子算子。然后using delta and d can define Laplace so 我们可以Laplace delta differential 算子就是上定义这个 delta 那欧米伽 k 到欧米伽 k。So omega k是the Topology joint. So delta alpha there is equal to alpha delta beta. 这个是用这个的性质可以导致这个的结果。OK， 然后所以这个棒，说的是棒镇定性，有棒镇定性是 delta alpha is equal to the alpha plus delta alpha like this。所以这个是semi-positivity， positive definite， 镇定性。然后 using 用这个 Laplace filtering 算子，我们可以定义调和形式 harmonic form。Like this way. The harmonic form 调和形式 ，omega 是调和形式，意味着 this omega 以 d omega is equal to 0 and then delta omega equal to 0。因为如果用这个的话，这个形式的话 ，delta alpha equal to 0， 意味着this is square d alpha is equal to 0 and delta alpha is equal to 0。因为这个有镇定性，有镇定性，我们可以说调和形式是 d alpha equal to 0 and delta alpha equal to 0。OK， 然后的非常重要的定律是 Hodge 微分decomposition theorem 分解定律。So omega k is equal to harmonic form plus d plus delta k plus 1 like this. Hodge decomposition theorem. So any 微分形式是 h plus d alpha plus delta beta. Okay. Can be written like this. 然后这个内积上它们增长 他们尖角，这个定义的证明需要非常高级的PDE 那个微分方程理论Warner's book， 它的这个 Hodge 分解定理的证明。So if you're interested, you can take a look. But I'm not gonna derive. I'm not gonna give the proof of the Hodge decomposition. We just accept this. 如果用 Hodge 分解定理的话，我们可以导致Hodge 定理，就是自然的映射 hk of m to hk drum H is mapped to homology， 因为调和形式是closed 的闭性式，所以there exists a natural map from harmonic form to drum cohomology. Okay. And in fact, this is the 这个是向量空间同构 isomorphism 同构向量空间同构，所以每一个drum 像同调类中存在唯一的 harmonic 调和形式为代表源。So the proof is very easy. It's easy to derive the injectiveness. So if you assume the H is equal to 0, injectiveness is if you use which means that the H is equal to d alpha. And if you use H d alpha, this is equal to, so this is H squared is equal to delta H alpha. Okay. Since H is harmonic form, this is equal to 0. So this means that so if you use 这个镇定式 so这个内积的镇定式 H is equal to 0. Okay. So this means injective. This map is injective. Surjective is also easy. If you use the Hodge分解定理 surjectiveness is the H any omega drum cohomology HK drum omega is H plus omega can be written like a H plus d alpha and then delta beta and then delta beta, and in fact omega it can be written like this is equal to H, the drum cohomology. So there exists always harmonic form that will give you the drum cohomology. So that's a very important theorem, Hodge theorem. And 然后如果我们用将Hodge theorem 的话，我们可以导致抛开对偶，抛开对偶。抛开对偶。 start for start. For map omega k of m drum cohomology 到 h n minus k drum cohomology of m 这里现在我们考虑这个 m 是compact compact is 经济右向 is compact and oriented 满头经济右向的流行黎曼流行向this map this map this is as normal 向量空间同过。因为 so there exists any harmonic form. This can be written as h which start h and this is always greater than z. 这个内积是背对non-degenerate 背对化所以 h is non-zero, which means the star h is non-zero. 这说明配对，这个配对和内积是非对化的，所以给出向量空间的同过。那我们可以一个例子，非常重要的例子 S1 的 drum cohomology S1 的 drum cohomology S1 的 drum cohomology 是非常简单的。如果我们考虑 0 degree 的 drum cohomology 相同调的话，这个是什么 ？drum cohomology is isomorphic to what? 0 drum cohomology 相同调。drum cohomology is the omega 0 of S1 是什么 ？omega 0 is a function 光化函数 ，okay? And then so drum cohomology is always defined by cross form the alpha equal to 0, but alpha is equal to dA. So cross divided by exact form. Exact form. So what is the cross form on S1? Constant function, good. And there is no area because 0 degree is the lowest degree. Okay, lowest degree, 最小的 degree. 所以这个是 given by constant function. Constant function. How about H1? If we use Poynter 对偶的话，这个是比 R isomorphic to R. Because 0 and 1 are dual to each other. It's one dimensional. So what is the 代表型？是什么 ？H1 的代表型。代表人 代表元 H1 it's very famous. S1 is like this one. The omega 1 is one form. S1 one form. Detail. We will detail. 去 volume form. So S1 detail is 2 pi. So we will 这个是 volume。So 静止有形象volume form is always 代表元the top form 的drum topology top form 的代表元。So this is spanned by detail. Do you understand? Is it okay? 明白了吗？因为 this Taylor is defined from 0 to 2 pi. Okay? 0 to 2 pi. So if you come back, you have a 2 pi. So it's not functional as well. Because there's a smooth function. It's not smooth function because here you start with 0 and come back here you have a 2 pi. Right? At this point, it's no longer continuous. Therefore, it's not 光滑映射函数 ，it's not the 光滑映射。So therefore, it's not exact form. It's not exact form. You understand what I mean? So this volume form is not the D some function of D. Taylor is not functional as one. So therefore, it's not exact form. The other例子 torus. H n of T2 round homology. How to consider n is equal to 0 is again constant function. Constant function is the 代表元 n equal to 1. It's just product of S1 plus S1. So therefore, there are two d theta 1 and d theta 2. So this is S1. You have a S1 and S1. Torus is like this way. We have a S1, d theta 1, and d theta 2. D theta 2. So therefore, this is isomorphic to R2. And it goes 1. R cross R. Okay? And the top form is equal is isomorphic to R. It's spanned by d theta 1, which d theta 2. It's a volume form. Okay, volume form. Okay? And then let's consider Poincare duality of here. So Poincare duality, so constant function is always dual to top form, the volume form. Is that dual to? Okay. But here, the Hodge star of d theta 1 is equal to what? D theta 2. And the Hodge star of d theta 2 is equal to minus d theta 1. Okay. So there, under the Poincare duality, they are dual to each other. Poincare 对偶。下，这个第二个例子，然后这就呢，就也像第三个例子 ，Sm n dimensional sphere 球面。是这个。This is k is equal to 0 and n, and otherwise. You always have a Poincare duality between volume form and the constant function, but except that there is no drum cohomology true. So this is the another example. 有没有问题吗？那我们结束上一次的复习，然后以后今天 before going to the Riemannian geometry, Riemann 结合 I will talk about a little bit about SU2 and the SO3. This is 非常重要的离群。And SU2 SU2 是2 by 2 2 by 2 matrix. By 2 matrix, which satisfy this condition. So 如果是 A satisfy this can be written like this way, where the and then sorry, and also so 这个是 SU2 的圆。所以如果我们学 alpha is the complex number 复数 so A0 plus IA1 beta is equal to A2 plus IA3. Then this equation is A0 square plus A1 square plus A2 square plus A3 square is equal to 1. 所以 as a manifold 作为流行 SU2 是什么？对 ，This is the S3 三维球形。那 SO3 是什么 ？SO3 是什么 ？SO3 is 转圈群 R3 的转圈群旋转群 R3 is rotation in R3, and then this can be defined as A in M3 in the R quotient A T transpose equal to 1. And also determine A is equal to 1. So that's the definition, in fact. But it's very easy to see that the rotation is very, I mean, if you have rotation, so rotation 是非常简单的。So you define the axis of rotation, and then from there you can just define the rotational angle. So this is B and theta. So that will define the order rotation. Axis that will determine the rotational axis. Okay. So therefore, that's the element of rotation. So therefore, so you specify the axis B and the angle theta will specify element of SO3, element of S3. So therefore, and then moreover, so if you have a B and a pi rotation is the same as minus B and pi rotation. It's same. So if you rotate pi rotation in B axis, but if you go to the the opposite way and do the pi rotation, it's the same thing, minus pi rotation. So it's the same element. Okay. So therefore, if you start with 0, and then the B minus B. So try to go to D direction in theta. So the length is theta. Okay. This will specify the element of SO3. Okay. So if theta equal to 0, it's just origin. So that's the identity element in SO3. Okay, identity element in SO3 because there's no rotation. And as you increase the rotation of theta, so you just move to the B direction by distance with theta. Okay. At the end of the day, you go to the pi. Okay. So therefore, so the three-dimensional ball. So this will define the three-dimensional ball B3. Open ball. But at the boundary, so at the ball, three-dimensional ball. So this will define three-dimensional ball. And at each point inside a three-dimensional ball, that corresponding to the element of the rotation, okay, SO3. But the boundary, you have to be careful. At the rotation of pi in one direction is the same as the rotation of the opposite direction of pi. Because pi rotation from one direction is the same as the pi rotation in the other direction. Okay. So therefore, you have to identify this point and the opposite point, okay, at the boundary. Okay. So therefore, at the boundary, it will become RP2. RP2. Is that okay? So therefore, so inside you have B3. At the boundary, you have RP2. And in total, it will become, so plus RP. So that, in total, it become a plus at the boundary. So that for P3, RP2 is equal to what as a manifold? Do you remember? As a manifold, this is RP3. How to define RP3? You have a S3 mod opposite point, like this one. Suppose you have S3, this is not S3, S2, but suppose this is S3. So you have identified the northern hemisphere and southern hemisphere. You just identify opposite point. Okay. Then what's left is this part. And the northern hemisphere corresponds to this B3. And then at the equator become two-dimensional sphere. This is S2, and this is B3. And two-dimensional sphere, and then you just identify the opposite point. Okay. So therefore, that will give you RP2. So this point is identified this point, and so on. This point is identified this point. Okay. So therefore, as a manifold, SO3 is isomorphic to, is diffeomorphic to RP3. Is that okay? Do you understand? SO3 is the as a manifold isomorphic to SO3. Is it okay? And then, so we know the SU2 is as diffeomorphic to S3. Okay. So therefore, you can have a double covering. SU2 with SO3 is the 2-to-1 map. Because SO3 is RP3. RP3 is just a S3 mod, the identify opposite point. Identify opposite point. So this is called double covering. And then the map is, you can define a map very easily. Suppose you have identified R3 element in X1. So here we define it like this way. Like this way. So you just identify it. So the point in R3 with this matrix identify. And suppose you have a SU2 element. So this is U inside of SU2. you can map U. You map like this. And this will so this will preserve inner product. So for instance, so the inner product in R3 is the x. In fact, you can define x and y is equal to -1/2 trace x and y is -1/2 trace of x and y. You can define the natural inner product. R3 的内居的定义是这样的。So for instance, if you So for instance, if you take x squared and trace -1/2, and this is equal to again x1 squared like this. So this is natural inner product in R3. Okay. And if you do that, U x U inverse. So remember, so trace of U x U inverse, U x U inverse, and -1/2 is equal to -1/2 trace, and they cancel, right? So this becomes 1. And the U x squared U inverse. But instead of trace, you can put the U into right, and this is equal to -1/2 trace x squared. Okay. So therefore, this transformation will preserve the norm, the length of the length. So therefore, this will define the SO3 element. And in fact, this is 2-to-1 map. So this is S3 to RP3. RP3. S3. Now, for instance, the kernel is very easy to see. Kernel of this map is the one and identity element, and then minus identity. So plus minus 1 plus minus 1, the kernel. Because even if you put the -1 and the -1 inverse is -1, if you multiply them, it is +1. Okay. So therefore, it's just identity. It becomes identity element in SO3. Okay. So it's just a kernel of this map. It's just a element 2. So that will tell you that it's a 2-to-1 map. Double coupled. Okay. And a little bit, so 我们学过这个切空间的概念。So this is S3. At each point, you have a 切空间 T, P, S3. Okay. So we can also consider such a 切空间 for SU2 or SO3. the identity element. So S3 is isomorphic to SU2. And at this point, you can consider identity element. You can consider chip conjunct. That and chip conjunct has the Lie bracket. Okay. And then, if you consider T identity element of S3, and then with Lie bracket, this is called SU2 Riemannian. So it's a vector space, and often it's a vector space with Lie bracket will give you product structure. That will give you so-called Lie algebra. So be sure. And then you have the exponential map from Lie algebra SU2 with SU2 like this. So which map X to E to X. And in particular, so if you map like E to the Tx, so this will give you curve around the identity. So you have an X, element X in tangent space. This exponential map will give you curve. Like this. So this is the E to the Tx. So let's look at the algebra of the SU2 and SO2. For instance, so the Pauli matrix you can consider Pauli matrix, and the Lie algebra SU2 can be generated by I times sigma x, I times sigma y, I times sigma z. Okay. Sigma z. Okay. So if you do the exponential map of the so this is equal to 0, I, 0. And this is isomorphic to like this. Then if you do the exponential map of I sigma x, what would you get? Or maybe t. It's better to have a t parameter. What would you get? How do you do exponential map? This is equal to 1, 0, 0, 1 plus t times and so on. Okay. and this is equal to cosine t, cosine t, cosine t, 0, 0. And then here, what you get is that the let me think. This will give you cosine t plus I sine t, and then 0, 1 t. So this is the element inside SU2. So namely this is equal to cos t and I sine t, cos t. This is the generator. And then similarly, so e to the I theta y is equal to cos t sine t minus sine t cos t. Yes. And here e to the I sigma is equal to IT like this. Okay. These are generated of the, and this satisfies the following Lie algebra. So if you define the EI, then Ej is equal to epsilon ij k E. So this kind of reaction. So this is what you already knew from the theory of angular moment. Theory of angular moment. You will have this kind of reaction. And then RP3, if you consider SO3, okay, SO3 is isomorphic to RP3. Okay, and here RP3 is just you just identify opposite point, okay, of S3. So therefore, this locally identity element here, the tangent space is same as the tangent space as the identity of SO3. Locally it's same because this point and this point is identified. Okay, but the locally around here, SU2 and SO3 looks very it's exactly the same because it's just a V2 quotient. But around here nothing happened because this point is identified. Globally, as a manifold they are different. But locally around here it's the same. We can see the same thing. So the SO3 is a rotation. So rotation x-axis, y-axis, and z-axis. That is tangent space. So you can have a rotation of tangent vector like this way, then this will generate the E to be Jx is equal to minus sine t, cos t. This will give you the rotation x-axis. And the same thing, rotation y-axis, rotation z-axis, that will give you the tangent vector at identity element, at identity. And this will satisfy the following thing: J is equal to jk. So the Lie algebra means that G is tangent space with the Lie bracket will give you product structure. Other has the plus and then product. Addition and then product. And this, as a vector space, you have an addition, and this bracket, Lie bracket will give you product structure. So x, y, x and y is mapped to x and y. This will give you product structure. And the Lie algebra SU2 that is isomorphic to SO3. That's very natural because locally nothing changed as a identity. Okay. So therefore, often people just write down the SU2 is isomorphic to SO3 as a Lie algebra because time and space looks very similar. Any question up here? No, 没有问题吗? And then, in fact, this presentation of Lie algebra is called the spin one half representation. And this representation of SU2 or SO3 Lie algebra is spin one half representation. This is spin one representation. Okay, that's done. Spin one is 3 by 3 matrix. Spin one half is 2 by 2 matrix. And the base is open. In physics, is always right when spin up or spin down. Okay. And here you have a spin 1, spin 0, and spin minus 1 half. Those are the three-dimensional bases of the spin 1 representation of a Lie algebra. And so on. And then SU2 has spin, in general, J over 2 representation. J over 2 representation. Oh, sorry. Spin J representation, where J is half integer. J is the half integer. Okay. Okay, I think it's a good place to take a break. I think after break, I will 解释这个黎曼集合，黎曼集合。Let's take a break. Any question about the SU2 and SO3? Is that okay? So this is very important. This double covering is very important, SU2 to SO3. 充吗？继续吗？那今天的后面我们学习这个黎曼几何的基本概念。So 就黎曼几何是1854年的黎曼的演讲，开始了之后经由这个 Christopher Rich 的等人的工作逐步严格化，逐步严格化。最终 Einstein, so this is speaking. Einstein 用黎曼几何建立关于相对论。相对论。Okay, so 本讲以较为数学的方式介绍黎曼几何三代核心概念。So one is connection. 就联络。The other is 联络 or this is called 斜变导数，斜变 covariant斜变。Geodesic is 特地线。And then also parallel transform. So 这个是平行移动。Number 3， 曲率降量，曲率降量。So Riemann curvature. So this is the 曲率降。曲率降量。So these 3 concepts we will learn from now. So the way I'm going to introduce is a bit more like a mathematical way, not like the physics way of doing that. But I think that will eventually lead you to so-called these this notion will appear also this 向量层的理论。This Young-Mills or like a Carlton, Young-Mills and so on. This 向量层的概念也有这样的概念，所以我们用这个数学的方式介绍就是黎曼几何。那我们首先学习联络的定义。在光滑流行上，仅有光滑结构物以比较不同的切空间的相点。So you have a manifold. At one point you have a tangent space, 解空间。At the other point Q, we have another tangent space. Somehow we want to do the x and then do the y here. Okay. We want to understand how they are related. Okay. How they are related. Okay. So 比较不同的切空间的这种向量。To do that, we need to introduce so-called connection. So 联络是实现这比较的核心工具。You have a vector field, and then you just assign another vector field like this. So 这个是联络是一个映射。So two vector field to maybe I should use this one. Vector field is my notation. So 满足以下条件。Okay. So 以后的 x, y, z are the vector field, and f and h is a function. And it satisfies the following thing. 满足 f(x) plus hy of z. Okay. This is also the vector field. Okay. So this is vector field. So 这个是向量场的函数乘以向量场是向量场。这个是向量场。这个是infinity linearity. Okay. Number 3, Leibniz rule. Like this way. So x acts So x acts on function, you will get what? So if a vector field acts on function, you get the function. function multiply vector field, you get the vector field. So it's okay. And the vector field has a linearity, so you can add them up. Okay. So if this is they satisfy these three conditions, this is called Riemannian law. Riemannian law. And then the x, this is called so now the xy 成为 y 沿 x 方向的斜变导数，y 沿 x 方向的斜变的导数，斜变。And open, so if you have the local coordinate, so local coordinate del x, I. So I just write down like this way. Often people just write down. Like this. People just open it. And then this here I use Einstein convention. So implicitly sum over k is implicit. So I'm not gonna. I will always use the Einstein convention from now. Okay. So del I, del j are the local coordinates of the G 体，这是切空间的 G 体。So del I 的切空间的 G 体 acts on the another element of the G 体. You get the connection. This is called Christopher symbol. So 如果我们写 x is equal to xi del I, can be written. So if you use these properties, one can have the following. Like this. So here you can write down x is xi del I and y is yk and del k or del j. Okay. And use this property. For instance, if you use this property, one can just write down that x is out of all the derivatives, and then if you use for instance this property, you will get this part, and if you use this one, you will get this one. That's and then 在物理的文件，标示 物理的文献，物理的文献中，斜变倒数是 like this one, written like this. And this 意味着 del I y. Okay. This 意味着 this is del K, like this. Okay. So 物理文献中 always use the 局部坐标，局部坐标，所以这样写的 ，OK。那，这个 connection 在流行上满足上述条件的联络不唯一，对，这个好多联络满足这个条件，不唯一。但是现在我们不考虑metric 读量，不考虑，没有，我们不用读量，现在我们不用，但是引入黎曼读量后，可以从中选一个最自然的联络，最自然的。So suppose you have Riemannian manifold. Okay. 我们可以对，选一个最自然的联络。It's called Levi-Civita connection. Levi-Civita. Which satisfy the following. 度量相容性 metric compatibility. Like this. So this is the 度量相容性。Okay. So here you have a x and a y is paired by metric. Okay. So this quantity is what? Takes which one? This quantity is the pairing between two vector fields. So therefore, at each point you have some number. So therefore, this will give you the function. Function in acting on covariant derivative, you will have the two functions here. So one is the connection z acts on x, and after that you have another vector field, and then just take a pair. And the other. Number 2. Yeah, I mean, you can write down like this. Yeah, you can write. You're right. Dx on function. And the torsion free. So this is the exist uniquely. So this is uniquely exist. And this tonal free condition can be written as the follows. So if you use the local component, this will give you the delta gamma jk is gamma ji. And then here, and then if you use this one, acts on the local current, delta IGIJ is equal to so this is satisfied. Okay. So if you use this this rule, if you use this rule for local current， 主部坐标用主部坐标表示出来这样子。Okay. And if you use this property, in fact, you can write down Christopher sample is 1/2 GKL, and then delta I GJL plus delta J GIL minus. Okay. So if you use this property, one can just write down the Christopher symbol using metric uniquely, okay, in local coordinate. So 正确式的广义相对论是那个教材之中的定义。如果你看那个广义相对论的书，你应该看成这样的表示。Okay. 这是说到符号的标准公式是这样。Okay. So 雷利基的联络完全由度量占量决定。Okay. And here we use the inverse metric. So Gij inverse is Gij. Okay. Inverse matrix is Gij. And here we use the 非对话的关键作用。Okay. So the 度量是非对话 So the inverse matrix. So we use inverse matrix to define the crystal pattern. Okay. Now, 演出现的斜变导数与So if you have a curve, okay, so this 斜变导数so this is gamma and then you can have the x here, and you can have the covariant derivative is really, you can define like this. So gamma dot here is the speed in here, is a tangent vector here, gamma dot. And then covariant derivative along this curve 曲线的斜变道处有可以定义这样。So if you write down the local coordinate, so you can write down like this. If you use the local coordinate, you can have like this. So this okay. So here you have a local coordinate. So this gamma dot d dt can be written in a local coordinate dx1 dt and dx and d the local coordinate in the tangent vector. 用逐步坐标这个写变道数，可以有这样的表示。And then 如果用这个写变导数，写变导数的话，我们可以定义平行移动的概念。平行移动的概念是，如果this one如果 this is 0的话，x is the vector field x is parallel vector field along gamma 曲线 ，okay. So if this is equal to 0, so here vector field x is parallel to parallel vector field along gamma. Okay. And since it's an ordinary differential equation, so you have the if you have the x t equal to 0, if you have an initial condition, you can always do the power transport. If you have an initial condition, you can always do the current transport along gamma, and that will define the power transport 平行移动。Okay, is it okay? Do you understand? So if you specify the initial condition, then you can solve this differential equation ODE to have a solution along the curve. Okay. So 测地线 geodesic is the geodesic is the okay. Let me give you one example. Okay. So let me give you one example. So this is the suppose this is a curve, and then power transform along the sphere of the equator is something like this. Something like this. Or more precise, if you have like this kind of curve, you can have, if you have this one. Like this. Okay. Okay. Those are power transport along the curve. Is it okay? You can like you just do the power transport along the curve. And the equator, you just do the power transport like this. 然后这定线so given the Riemannian manifold, so one can define the curve. And the curve is called geodesic, or geodesic 测地线. If the gamma dot t is equal to 0. So this means that the okay. So at each curve you can have a tangent vector to the curve, the speed of the curve. And you can do the product covariance derivative along the curve. Okay? If they satisfy, and local coordinate 在具左标下测地线满自测地线方程。Okay, so they satisfy this equation. So it's easy to derive that one. So 现在 this maybe I should sorry this is very misleading. So this is capital X. Sorry, this is capital X, and this is local called small x, and this is capital X. Sorry about it. It's very misleading. This is capital X. The vector field X, maybe it's better to use Y because it's misleading. So this is Y. Like this. And then here, now we just have yk is equal to dxk dt. So that's tangent vector along the curve. Okay. So这个方程北腔外这个测地线方程 is 这个关于就坐标的二阶强微分方程。So for instance, in S2, what is geodesics? Geodesics, you can just have the geodesics is always the gray circle. It's also gray circle. So always the geodesic is the in Riemannian manifold. You have a P and Q. P and Q. And then if you have a P and Q, you can consider all the curves, but the geodesic is locally the shortest path, shortest curve. And then in the in the sphere, it's always like a great circle. It's always great circle. And in fact, so the reason why you can get the shorter distance that so if you have S is given by the element from P and Q, and the curve along So if you consider this action, it's just measure the line element from P to Q, and they solve the Euler-Lagrange equation. You can obtain this geodesic equation. That's much. Okay. However, so this is the only. So given the initial condition, so the initial condition here. Initial condition is this is gamma naught. Is this given the initial condition, one can always solve this geodesic equation, okay, to locally, and that will give you the locally shortest path. But globally, it's not the case. For instance, if you start with here, okay, and if you want to go here, this is the shortest path. This is geodesic, but you can always have you can circle around to come back to this one. Okay? This is also satisfies geodesic equation, okay? But it's not shortest path because you just circle around. This equation, this curve also satisfies this geodesic equation, but it's not shortest path. So it's always give you the solving this equation always give you locally the shortest path, but globally it can be it can be longer. It can be longer. Okay. Any questions this moment? Okay. Okay. So now we will introduce the notion of Riemann 曲率占量 Riemann 曲率占量 So if you have a current transport in curved manifold, so in flat space R2 flat space, If you have the what is the geodesics? Straight line. It's just line. So those are the geodesics. And then here, if you start with some vector field and do the parallel transport, if you come back, you always have come back original thing. However, curve manifold. If you consider curve manifold and all of those are geodesics, okay. If you start with this vector field and do the parallel transport, you can always have do the parallel transport. So if you come back by parallel transport along geodesics, you always have the initial vector and the final vector is different. Okay. So if the curve, the manifold is curved, somehow it's non-trivial, it's not flat. You can there's a difference between initial vector and final vector by doing parallel transport. It's because the manifold is curved, and this curve这个曲率占量可以measure 测这就curve 的意思 ，OK， so 曲率。And then and this curvature x and y, yeah, so the curvature R you have a assignment. So this x, y, and z. So the vector field is mapped to another vector field, like this way, which subtransform which is defined as follows. Like this. Okay. So if the connection acts on vector field, you get another vector field. Again, you can act another connection to the vector field, you get another vector field. And you can take the you swap x and y, and then just act on it, and take the Lie bracket and again act on it. And those So this will define the Riemann curvature 区域区域 and again if you write down the if you write down local coordinate, one can write down like this. So this is the open 广义相对论的述本，用这个逐步坐标的标尺。Okay. And then if you write down like this, since the nabla, so the local connection or like a covariant derivative always can be written in terms of the Christoffel symbol. So this one can be written. LGK. Like this one. So this is a local coordinate. And you can easily see from here, so this part will give you this one, and this part will give you this one, and this part will give you this part. As you can easily see. So you just set the x, y, and z are like this one, and use the ordinary way of writing the Christoffel symbol covariant derivative. You will get this expression. So this is again the 区域将量，区域将量，是偏漏的非交换性。So for instance, so here you first do the covariant derivative y, and next covariant x is more like you just do the around the x direction. You just do the parallel. Around x direction, you have a parallel direction, and the y direction, you have a parallel transport of z. Or you do the first y, and then you come back to x. And then if you do somehow the space is curved, this parallel transport will give you slight difference between them. So this is now the y nabla x and z. This is z, and here nabla say x nabla y and z. And then you just take a difference between. It seems like something like that. And with this quantity. Okay. So 这个区域占量的对称性。 So okay, so far, so this definition do not use the metric here. So here, one can define any connection, one can define this topology. Okay. But if you use the Riemannian metric, Riemannian manifold, and nabla is a La Vicevita connection. And then one can define the Riemann curvature. And then it satisfies the following condition. This is obvious. And then the other反对称性是this is the R I J K L is equal to minus R I J L K. So this is R I J K. So just use the this upper symbol here to bring it down. To bring it down, you use the metric 度量。用度量，我们可以定义 R I J K L。然后 another thing is this one R I J K L is equal to minus R J I K L. And symmetry and number 4 is Riemannian. Okay, so this is a PMJ. Okay, so it's a PMJ. Okay. Sorry, I think I skipped some of the part of the. Sorry, I think this is not a good way of defining. Sorry, I somehow skipped some of the important concepts. Sorry, this is not the right way to do that. Sorry about it. So another way of defining the Riemann curvature is really literally as follows. You have an x2 part like this way. Yeah. To the vector field, like one can always have the like a P and S define the family of curves like this way, family of curves like this way, and then Riemann curvature. ds on x is equal to x like this. So this is a curvature you get. It's a difference between two ways of doing the parallel transport. So this is literally the one way to define the Riemann curvature. And if you use this property, so the important property the Riemann curvature should satisfy. So this will be Riemann这个like this. So this is a very important property. So the reason why we add this is to satisfy this condition. To satisfy this condition. Okay. Okay. This. So therefore R Y J del J del K VK. So you come like this. So if you use this property, one can always write down the you can bring x, y, z part out of the out of this Riemann curvature. So the reason why we add this term is really to satisfy this condition. To satisfy. If you don't have this term, you won't satisfy this condition. Any question at this moment? Okay. Sorry. So here, I'm sorry. I made a mistake. The way I think I should. So here to introduce notion, I can define x, y, w is equal to g. Okay, so if you define this pairing between this vector field after the applying curvature and another vector field and take a pairing using Riemannian metric, you get some function. And this will satisfy the following thing. And this is first Bianchi identity. And there is second Bianchi identity. So this is the second Bianchi identity. So derivation is quite straightforward. If you use the definition of Christopher sample and use the differential curvature, one can derive all the properties, which I leave it to you as an exercise. In terms of local coordinate, it's just equivalent. This one is equivalent to this one. This one is equivalent to this one, and then so the fourth one is the same as R L I J K plus R L J K I plus R L K I J is equal to 0. Okay. And then also the second, this is the fourth one. Number 5. So this is R, L, K, I, J, S. This is the covariant derivative plus L, K, J, I, no, J, S, I, plus R, L, K, S, I, J, equal to Z. So that's second Bianchi identity in local point. 用逐步坐标，我们可以实践的。然后one can define the Ricci 占链 is our just contraction between first and third the tensor. And also furthermore, so this is Ricci tensor. R is defined by R I. This is the scalar curvature. Okay. Scalar curvature. Any question at this moment? Okay. Okay, any question at this moment? One way to understand the so one way, so the one thing, if I consider Riemann curvature, so one can define Gauss curvature. So this is called Gauss curvature. This is called Gauss curvature in the Riemann surface. In Riemann surface, you have a coordinate. Riemann surface. It's a two-dimensional surface, and you can define metric on the surface, two-dimensional surface, and then compute all the quantity, and using definition, and you look at the 1, 2, 1, 2 element of the Riemannian curvature. And this is the non-trivial one, and then if you divide it by determinant G, one can determine the Riemann curvature, and then if you do that, you can have other characteristics. Also, this is Gauss-Bonnet theorem. Gauss-Bonnet theorem. This is called Gauss-Bonnet. So this is very important theorem. Left-hand side can be defined by differential geometry. So you need to introduce a Riemann surface, and you need to introduce the smooth structure and the metric, and you need to compute all the Christoffel symbol, Riemann curvature, and then finally you can obtain this Gauss curvature. So it's really left-hand side of differential geometry. So left-hand side differential geometry. This is we need a wave G. Right-hand side is the topological quantity, Euler characteristic. So the Euler 气性数，这是椭破不变量，所以就是椭破不变量。So this is the 椭破不变量。demasiada por igual and this kappa can be using a local quantity. So that each point you have to do the derivative of the metric and so on, and then you can define this Gauss curvature. And in particular, I didn't write it down, but I can write down the this yeah. Okay. And the kappa, so this kappa really depends on the metric. So you can choose how you define the metric. So for instance, if you embed the torus inside here, like this way, or you can embed like a torus like this way, it's very, very like that. The induced metric from the R3 is different. Okay? So this curvature is really like higher than this one. This one. Curvature is bigger than this one. It's more like bented. So curvature is different. But if you integrate out, you get the same number. Okay? Same number. So therefore, it's a very, very magical theorem. Gauss-Bonnet theorem. So So here kappa is locally defined, but integrate out the entire surface, you get the global quantity. So another way to say this, the importance of this theorem is from local quantity to get the global information. Local quantity. So yeah, that's one thing. Okay. So yeah. For instance, example. So you just consider S2 and standard metric. So this is standard metric. Standard metric. And then the kappa volume kappa. So this will give you kappa to be 1 in fact. Kappa to be 1. And the volume form is equal to D both saving, D saving, D phi. And then you can integrate out 1/2 pi and the volume form. And this will give you the area of the sphere. Okay? Area of the sphere is 4 pi. So 4 pi, this will give you 2, which is the Euler characteristic of S2. Okay. So this is multiple magical theorem. And then in the case of torus, you can just have a flat metric. So you can have a flat space and then identify the edges, you get the torus. And it's a flat, so curvature kappa is over 0. So therefore, Euler characteristic of T2 is 0. And in general, if the Riemann surface G, this is 2 minus 2G. G is the genus. So I forgot how to say genus in Chinese. quick 记的一般surface 曲面的我的序形数是 2 minus 2g. Okay, any question at this moment? Okay. So now I think the important thing is that the Einstein equation okay, so let's introduce so-called Einstein equation. OK， so 如果我们考虑OK， and then maybe I should mention something a bit more. Yeah. So the higher generalization, higher dimensional generalization of this one is considered Chang Shengchang. I think one of the most famous mathematicians in China. Chang Shengchang try to generalize this Gauss-Bonnet theorem to higher dimension 2n to get this Chang class or Euler class and so on. Euler class and so on. So yeah, that's another generalization. And also, further generalization is given by Atiyah and Singer. Atiyah Singer index theorem. 这个G标定理 that's also the generalization of Gauss-Bonnet theorem. Now we can consider the Riemann-Hiller action. So 作用量。Okay, so one can consider on the Riemannian metric, one can always Riemannian manifold. One can always compute this scalar curvature, and gamma is constant. This is called cosmological constant, and this is the scalar curvature. And take the variation with respect to metric, and then what you get is that you get this one. Okay. Okay. You will get this one. And then if you add something called matter field, so here you have the curvature of spacetime, and here in spacetime one can have whatever field, like electromagnetic field. So since the reason why you can see this blackboard is that the photon, it just hits blackboard and it just go to your eyes. Okay? Those are electromagnetic field. Or whatever. So we have a desk, those are atoms, made of atoms, molecules, and so on. So those are all described by some field. So describe some field, and using that field, one can define this action. For instance, if you have an electromagnetic field, the action of the electromagnetic field is given by square root G d for x f mu nu f mu nu. Okay? And f mu nu is in fact given by del mu a mu minus del mu a mu, like this way. And one can using a metric, one can take a Hodge star and take wedge. So like this. This is the action of that. And then if you take the matter field with respect to G mu nu. Oh, sorry. I think I have to properly normalize. you get the following quantity, T mu nu. So it's a stress energy tensor. It's called stress energy tensor. So the Einstein equation becomes something like this one. It's equal to h pi g T mu nu. So left-hand side is a quantity that measures the curvature of the space-time. The right-hand side is the energy or momentum, or that measure energy and momentum of the field that describe matter or whatever. So therefore, this Einstein equation will tell you that the curvature of the space-time is determined by energy or momentum of the matter, or like the field, something else from the gravity. Okay. That's the Einstein equation. So 19, Einstein derived this equation in yeah. So 左边集合链的集合链那个时空的区域将向这个有就血线血线有就血线，右边是无际物质云的浓点的分布，物质浓点的分布。So that's the Einstein 的本质。Okay, so 无际告诉时空如何弯曲，时空告诉无际如何运动。Okay, that's the miracle of Einstein equation. Okay, let's stop here. And then next time, I'll a little bit talk about the consequence of Einstein equation and so on. It's called tidal force and so on. How the tidal force is measured by Riemannian curvature and so on. And after that, I'll talk about a little bit simplex geometry. 新几何. Okay, let's stop here.无际。